Hello everyone, welcome to this presentation. Today we would like to discuss about our project Relationship between Food Habits and Diseases under the guidance of Dr. Brian Hammer. Let's first start with a discussion of our project team that worked on this project. I'm Ankita Khurana from Industrial Engineering and Management along with Rahul Sati and Shubham Singh from IEM and MSIS departments respectively. Going through the presentation now, I would like to begin with the introduction of the project, followed by objectives and methodologies used to do the project, the expected benefits of the project and the intended beneficiaries. We'll then move it to the next level by discussing the project scope, where we'll go through the project goals, deliverables and some of its limitations. We'll then discuss the data preparation phase, followed by its exploratory data analysis and the modeling techniques that have been used to do the analysis. Once we are done with the description of the project, we'll talk about the results obtained. And then we would like to end the presentation with the future scope and lessons learned. Now, starting with the introduction, the project deals to discover an association between the type of food that people consume and the prevalent diseases. Chronic diseases like obesity, diabetes, etc. are long-term diseases that are not contagious and largely preventable. They make up to more than half of the worldwide deaths each year, which is about 35 million out of 58 million. In our analysis, we are looking at the deaths caused due to these diseases in 113 countries between the year 1979 and 2011. We'll explore if these food habits is one of the preventive measures to bring down the risk of certain diseases. Now moving on to the objectives. The objective of our project is to explore an association between the type of food that people consume and the prevalent diseases, to identify major diseases causing maximum number of deaths across various countries, and to identify food items leading to a certain diseases and to discuss how it can be prevented. Now coming to the methodology part that we have used cross-industry standard process for data mining or CRISP-DM methodology for our project. We'll now move to the benefits and beneficiaries. Our project would benefit organizations like WHO, national health organizations of different countries, and other healthcare organizations. Our project would also be beneficial for health insurance industries. Through our project, hospitals can also be benefited. They can allocate their resources to fight the diseases that are more prevalent in a particular region due to the food habits in that region. We'll now move ahead and we'll discuss the scope. Coming to the scope of the project and owing to the time limit given to us, we narrowed down our focus to the top 6 diseases, which we selected based on Pareto chart analysis. Our model can predict average number of people that will be affected by the particular disease given the food consumption statistics of that region. But it will limit to predict whether a person will develop a particular disease given the food types he consumes. Our project is limited on the basis of death and food consumption data for 113 countries between the years 1979 and 2011. Our project would also be limited to determine the nutritional content of the food on the cooking methods that we have used. Now we'll move to data preparation phase. In the data preparation phase, we have five steps. We'll discuss each of them in little detail. The first one is the data access. For the food consumption data, we relied on FAO-STAT, that is Food and Agricultural Organization of the United Nations Statistics Division. The food and data information that we have contains the information of each food type like wheat, rice, etc. for all the years between 1961 and 2015. This is the website. The diseases data we collected from the World Health Organization website. We had 31 diseases in total that were available to us in .xml format between the years 1979 and 2014. It contained the name of the country and the number of deaths due to that particular disease in the descending order. Let's now move to the data consolidation phase. Since we had more than one data source, we had to consolidate all the data collected into one file. There were 31 sets of diseases that were combined into a single file. The columns that contained item, element, and unit were concatenated into a single column. Both the data sets of diseases and food consumptions were then consolidated into one single Excel file. Now moving on to data cleaning. In the data cleaning step, some of the blank rows were removed using the code in SAS. Rows where population was blank were also deleted. We moved the years for which the data was not available in both the data sets. And after removing those years, we were left with the data for the years between 1979 and 2014. Moving on to data transformation, we had to transform a data for our analysis. So we reshaped the data by transposing some rows and columns. And for this purpose, we used SAS 9.4. After the removal, we were left with 113 countries, and new columns for each diseases were introduced using the formula number of deaths into 10,000 divided by population. We used logarithmic or square root transformation on our variables. Coming to the data reduction phase, we considered only those countries that were common to both the data sets. Certain columns that were not necessary were removed, and after the removal, we were left with 113 countries. We'll now move to exploratory data analysis, and I'll hand over the presentation to Shubham Singh to explain this part.
Thank you, Ankita. We will now look at the exploratory data analysis. Descriptive analysis was generated using the IBM SPSS modeler. There were certain variables which were dominated by a specific value. This could have affected the analysis, and hence these variables were deleted. Exploratory analysis was done using Tableau. The graph below shows the proportionate number of deaths due to diseases for different years. It can be seen that it drops to a very low value for 2012 and 13. This does not seem okay, hence these 2 years were removed from the study. The following bar diagram shows the proportionate number of deaths due to each disease. 3 diseases causing maximum number of deaths were malignant neoplasm, ischemic heart diseases, and cerebrovascular diseases. The following plot shows number of deaths caused by these 3 diseases in each country. It was found that these 3 diseases cause maximum proportionate deaths in countries like Netherlands, Hungary, and United Kingdom, which have high development index. These countries have made enough progress in their health services so that the proportionate death due to the other diseases which are caused by unhygienic conditions or lack of vaccinations are low. Data splitting was done using IBM SPSS modeler in the ratio 70-30. This provided ample data for both training and testing. Both training and testing dataset have approximately similar descriptive statistics. Disease prioritization was done using the Pareto chart. It was found that 80% of deaths is caused by 20% of diseases, that is 6 diseases. As all the variables were continuous, we chose multiple regression. Neural network was chosen because it can handle any nonlinear functions. And decision tree was chosen because we wanted to have some classifications and splits based on independent variables. Modeling assumptions. Linear relationship exists between the independent variables and dependent variables. This was confirmed by plotting the residuals of independent variables. Correlation matrix was plotted, and it was found that independent variables were not highly correlated among each other. Also, the residuals were normally distributed, and this was found to be true. The following picture shows the flow diagram of the model. Coming to the target variables, first ischemic heart diseases. We chose the 10th model consisting of 10 variables. It explained 70% of the variance in the model. It can be seen that oranges, rice, and maize has negative coefficient. The neural network model was 91.5% accurate, and the three most important variables were fruits, eggs, and beer. In the decision tree output, it can be seen that the first split was obtained by the variable rice, and the next by potatoes and potatoes. Malignant neoplasm. We chose the sixth model, which has 6 variables. It explained for 80% of variance in the model. It can be seen that there were no negative coefficients. The neural network output was 94.9% accurate. The three most important predictors were pig meat, beer, and potatoes. The decision tree output in the decision tree output, the first split was obtained by the variable pig meat, and the next was obtained by potatoes. Cerebrovascular diseases. We chose the 10th model consisting of 10 variables. Fruits, tea, pineapple, and mollusk had negative coefficients. The neural network model was 90.5% accurate, and the three most important variables were fruits, wheat, and eggs. In the decision tree output, the first split was obtained at potatoes, and the next were obtained at wheat and pineapples. Diabetes. We chose the 13th model, which consists of 13 variables. Potatoes, fish, eggs, oats, coffee, and tea had negative coefficients. In the neural network output, the three most important variables were sugar, poultry, and bananas. This model was 76.1% accurate. In the decision tree output, the first split was obtained at poultry meat, and the next were obtained at population and poultry meat. Pneumonia. We chose the 10th model. Poultry meat, bovine meat, offals had negative coefficients. The neural network model was 77.0% accurate, and the three most important variables were mutton, poultry, and maize. In the decision tree output, the first split was obtained at vegetables, while the next split were obtained at spices and fats. Chronic lower respiratory diseases. We chose the 13th model, and infant food, cereals, barley, and offals had negative coefficients. The neural network output was 86% accurate, and the three most important variables were starchy roots, spices, and oranges. In the decision tree output, potatoes had the first split, while infant food and animal fat provided the next splits. For the remaining part of the slides, I'll hand it over to
Thank you, Shivam. These models were great learning experience. Let us now move to the next phase of our presentation, that is results and assessments. Coming to the multiple regression model, here's the equation that we used for explanation as well as the prediction. For schematic heart disease, it can be seen that the oranges, rice, and maize products have negative coefficient, which means that higher per capita consumption of these food types reduces the proportional number of deaths by this disease. Hence, they should be consumed in greater quantity. But for the potatoes and alcoholic beverages, they have a positive coefficient, which means that they should be consumed in smaller quantity. With a similar analysis for the rest of the diseases, we came to the following results. For malignant neoplasm, alcoholic beverages, potatoes, and pig meat should be consumed in smaller quantity. For cerebrovascular diseases, fruits, especially pineapple and tea, should be consumed in greater quantity, while potatoes, pig meat, wheat, and alcoholic beverages should be considered in smaller quantities. For diabetes, eggs, oats, tea, coffee, fresh water, food, and potatoes should be consumed in greater quantity, while poultry meat, peas, pig meat, and sugar should be consumed in smaller quantity. For pneumonia, although the model explained only around 30% of the variance, the variables included in the model are significant. Offals, fruits, bovine meat should be consumed in greater quantity, while grapefruit, maize, and eggs should be consumed in smaller quantity. For chronic lower respiratory diseases, it yields an interesting result which can be related to smoking. Infant food has a negative coefficient which signifies that if the consumption of infant food is large, the proportionate number of deaths due to chronic lower respiratory diseases is less. This unusual relationship can be easily understood as infant food consumption means that there is a presence of infants and adults generally do not smoke when they are around. So, if the parents of the infant smoke, they may give it up temporarily or permanently. This giving up of smoking leads to less proportional number of deaths. Now, coming to neural networks. For ischemic heart diseases, based on predictor variable plot, fruits, eggs, and beer are the most important variables. Similarly, we have obtained the results for the rest of the diseases. Now, for decision tree, we have again used the same approach. From the predictor importance plot, we get the following important variables, and the results are as follow. Next, we come to assessing the model. We use the analysis node of IBM SPSS modeler for model assessment. The selection criteria picked is mean absolute error. The lower the value, the better is the model. We picked mean absolute error as it is less sensitive to the occasional large error, and calculation of MAE is relatively simple. For the 6 target variables, we have compared the mean absolute error. We can see from these plots that MAE is least for the neural network model. So for prediction purpose, we will be using neural network. However, for recommending what to eat and what not to eat, we will be using multiple regression. So hence, neural network proves to be the best model. Now, to talk about original prediction versus delivered outcome, we narrowed down our scope from 31 diseases to 6 diseases. Here, it was not expected that only 6 diseases will account for the 80% of the total deaths. And we did not expect the model to explain the extent it did in case of chronic lower respiratory diseases and pneumonia. Although there was no direct relationship between the food type and the disease, it is highly possible that there is some sort of indirect relationship which is being manifested and has been depicted in the model. Coming to the future scope, the horizon of the project can be broadened in various ways. This project can take a wider horizon by including various other diseases as well. Also, factors like pollution and socioeconomic factors can be included in future. This will improve the model as deaths also depend on these factors. Now, coming to the lessons learned. Throwing all the variables at the model without transformation and cleaning isn't going to yield a good result. Regression model can be overwhelming if all the variables are entered in the model at once. Knowledge and good understanding of domain is very essential for the project to be successful. Also, pruning of decision tree is required to keep the output concise. Now, we come to the end of our presentation and hope you all like it. We would also like to take this opportunity to thank Dr. Hammer for guiding us throughout the project by clarifying all our doubts and also giving us timely suggestions. Thank you.